Hello class, welcome to chapter 11, the last chapter of this course. Looking at 11.2, we start with this section, evaluate and graph exponential functions. And we have these two objectives, which is to graph and also to apply these in application situations. So let's understand what an exponential function is. It's pretty straightforward. We know the word exponent is related to the power, so you can see that this equation also is related to the power. Now, we have used the word power and exponent interchangeably, right? But I do want to bring to you a subtle but significant difference between the two. Okay, now if I say x power 2, right, I like to use the word power when the power is a number, okay? Now, if I have 2 power x, then the power x, I would rather call it as exponent because it's a variable, okay? So let me make that quick connection, okay? We call it power if it is a number, any number, fraction, negative number, anything. And we call it an exponent if it is a variable. This is a subtle difference. I don't think people consciously use them as this. But I just want you to understand that the exponential function, that word comes from this understanding. When you have a number in the power, that is computed using the powers, like squares, cubes, and so on. And if you want to undo that power, like if I want to remove the square from the x, I just want to find x, we use the square root property, okay? So we had a way to undo it. That's something we learned mathematically. Now, when it comes to exponents, we are trying to solve x that is sitting in the power, right? So it's not as easy, actually. It is very complicated to access that x which is in the power. So we use this exponential function and we learn about these properties. And we're going to also learn about what property or what concept should be used to undo the x. Because if you are trying to bring down the x to solve for x, we can't do it at this time, okay? So anyways, coming over here, we're saying your function f of x is a power x, okay? X is the variable. A has some restrictions. A must be positive. You can't have a negative a. Also, a must not be 1. That's kind of trivial, right? If a is 1, 1 power x, 1 power anything is 1. 1 power positive power number is 1. 1 power negative number is 1. Even 1 power 0 is 1, right? So you don't want a to be a 1. So that is clear, but we want a to be positive. So let's remember that. All right, let's graph this. Now, even before that, let's discuss the shape. What do you think is going to be the shape for an exponential function? Well, think of it in English. Exponential. Exponential means to grow rapidly, right? Or to decline rapidly. Okay, something grows exponentially. If you can think of it, it just means that something picks up slowly and then, grows rapidly. Okay. In my mind, an airplane takeoff is what comes. Okay. So an airplane takeoff taxis slowly like that, and then it suddenly lifts up and it picks up speed and then altitude and so on, right? So this is how the shape of an exponential function looks. It is not a line. A line is steady growth, right? It's very predictable. But exponential function climbs rapidly, okay? Slowly here, and let me write that here, and rapid movement in a quick period of time, okay? So that is the kind of shape we're going to expect in these graphs. So they're asking us to graph f of x equals 2 power x and g of x equals 3 power x on the same grid. Okay, now because we expect a curve, we always go for 5 points, okay? So let's say, again, you want to start with -2. Again, remember your base is a 2, okay? So let me say this table is for f of x equals 2 power x. So it's 2 power x. Okay, your base is fixed. It's not a negative number. Everything is good. So it's the x that you're trying to fix for different values. And x can take negative or positive values. We've done that, right? x can have a negative exponent. The power can be a negative exponent. So negative number, we know how to handle it. Again, this goes back to the rules related to exponents. All right, so it's 2 power x, right? So it's 2 power negative 2. This is 2 power x, 2 power negative 1, 2 power 0, 2 power 1, 2 power 2. That's what we're trying to do. If you have a negative power, if you recall, we said flip the base, change the sign. So 1 over 2 squared. Okay, I flip the base is 2, I flip it, and I change the sign for the power. The power was negative 2, I changed it to a positive 2, which is 1 over 4. So it's negative 2 comma 1 over 4. Again here, negative exponent, so flip the base, change the sign, which is 1 over 2. Negative 1 comma 1 over 2. These are positive powers, so no problem. Anything power 0 is 1. We know this from 0 exponent rule. So 0 comma 1. 2 power 1 is 2. 2 power 2 is 4. So 1 comma 2, 2 comma 4. Okay. Let's go ahead and graph this one. Negative 2 goes to 1/4. See, now I have to look at my box. Each box is 1 unit, but I have to mark 1/4 of a unit. So that means you have to eyeball this and kind of roughly divide this into, into 1/4. Something happened with the Zoom, I think. Okay, let's fix it here. Okay, negative 2 and 1/4. I'm eyeballing it to be the fourth part. Let me see if I can label it. It's going to be pretty close, so that's okay. Negative 1.5, so that's going to be smack in the middle of that box. Okay, negative 1.5. Then we have 0 comma 1, which is on the y-axis. 1 comma 2. You can see that right after it crosses the y-axis. Once it crosses the y-intercept, picks up speed. 1 comma 2, and it climbs rapidly. 2 and 4. Just for you to see, if I had chosen a 3, right, this would become 2 power 3, which is 8. 2 times 2 times 2. That will be 3 comma 8, and you can actually see that it will be 3 and 8 all the way up here. Can you see how quickly it climbs? It's indicated by the vast gap between the points once it crosses the y-intercept. So let me I know it's a graph that's going to go all the way up here. So that's going to be f of x equals 2 power x. So we graphed one of them. Then the other one was g of x, which is 3 power x. I suppose, yeah, 3 power x. So once again, let's furnish values for x. Negative 2, negative 1, 0, 1, 2. And see, I can put the 3, but I will tell you when we get to that how difficult that will be to even graph that here. All right, so 3 power negative 2, 3 power negative 1. You're plugging in for x, right? X is in the exponent. So 3 power 1, 3 power 2. Okay, flip the base, change the sign, 1 over 9. Flip the base, change the sign, 1 over 3. No change here because these are positive powers. 3 power 0 is 1, but this is positive. 3 times 3 is 9. So our coordinates are negative 2 comma 1 over 9, negative 1 comma 1 over 3, 0 comma 1, 1 comma 3, 2 comma 9. Okay. I wanted to use blue, but on second thought, I'll switch to red because your markings are blue as well. Okay, negative 2, and we're supposed to do this on the same grid. So negative 2 and 1/9. Now I have to divide this box into 9 equal parts. So my 1/9 looks pretty much touching in my negative 2, but you know it's a little above that. So negative 2 and 1/9. Negative 1 and 1/3. So I'm trying to break this into 3 parts. Okay. So this is broken into 3 parts, so it's going to be a little above the half point, right? Oh, no, that's 1/3. I'm sorry. Okay. -1 and 1/3. And then we have 0, 1, which coincides with the other one. So 0, 1, I'll put it in red there. 1 and 3. Put it 1, 3. 2, 9. Now that's way out of the scope. Okay, so perhaps 9 was somewhere there. 2, 9. So you can see that's why I could not do the 3. So if I did the 3, it will be 3 cubed, which is 27. And there's no way we could fit that in our particular grid. Now it's time to connect our dots. See, this dot on the top is incorrect. Okay. The thing is, if I attempt to erase it, it might erase the other things. But let me see. Okay, good. We now connect these ones. So as you can see that this climbs faster. This one's climbing faster than the green, but this one started slower than the green. Right? And this is g of x equals 3 power x. This started slower, but then it climbed up faster once it crossed the 0, 1 mark. So as you can see, you can recall this as if it was a plane takeoff, right? It taxis slowly and then it climbs up rapidly. And that's your exponential function here. And we're looking at a different base. And what you notice is if your base is bigger, it climbs faster. Okay, the climb is steeper. And that's what is illustrated in this particular exercise. Let's look at this in real life examples. In an exponential model, we can see the role of compound interest. The role of exponential models in compound interest. This is to do with business. Well, compound interest is the way our credit cards are charged. Okay, it's interest upon interest. That's why the word compound. To compound means to add on. So compound interest has 2 parts in it. Now, when we are able to numerically give the number of times something grows, then we use the n, this formula, the first one. Okay. So when it's compounded n number of times, we use this formula. Now, when we have something that's compounded continuously, think of it as life. Okay. In life, things grow continuously, right? A baby that's in the mother's womb, that baby grows continuously. It doesn't grow once a day. It doesn't grow once a minute. It doesn't grow once a second. It grows every moment, instantaneously, right? And even when the baby is born, it continues to grow. So when do we know it started growing, right? So we don't know the starting point when it started growing, but we do know that it must have started at conception, right? That's when the baby got its life, and so it's growing since then. And so when does the growth end? Well, we grow up and we grow older and all that. The growth still continues, and then when we die, does the growth stop? So we might think, well, when we die, the growth ends. Yes and no, because after we die, it's exponential decay, literally, right? We decay, we decompose our body. So that's also a kind of growth. It's negative growth, but that's also some kind of growth. So you can see that in life, right? Anything related to life, the growth is continuous. The compounding is continuous. It's cannot be measured by a certain time period. And because of that, we use this second formula, A equals PE power RT. So now we'll look at this problem and try to see how this can be computed using the specific formulas. A total of $10,000 was invested in a college fund for a new grandchild. If the interest rate is 5%, how much will be in the account in 18 years? And based on these compounding periods. Okay. All right. So let's first, write what we have. So we have 2 formulas, A equals P times 1 plus R over N, the whole power NT. Your A here represents the new balance. Let me write this down here. Because understand the story, right? We're investing $10,000 for a college fund for a grandchild. So we want that to grow for many years, in this case for 18 years, so that you can expect a growth in that investment. And so the new balance, you want it obviously to be way more than 10,000 that you invested 18 years ago. So that's the new balance. It's kind of the future balance, right? P stands for the principal, the amount that was invested or borrowed. Principal, amount, amount invested or borrowed. Okay. R stands for the rate of interest. N stands for the compounding period. This is something we're learning here for the first time. Compounding period. What this means is how frequently do you want the interest to be charged or the interest to be given to you? In this case, it's investment, right? So we look for the number of compounding periods in a year, okay? So if it is n equals 1, if it is yearly compounding, n equals 2 if it is semi-annual or half-yearly, n equals, let's say, 4 if it's quarterly, right? Every quarter, I think I got it wrong, quarterly. If it's monthly, n is 12, and so on, right? So it depends on the frequency, and so this is a compounding period. T stands for the duration of loan or investment. Now, when it comes to A equals PE power RT, obviously the N is removed because you can't really count, right? How frequently something is growing, you can't really count that. So instead we have this E, that's the big clue here. All others are the same, A, P, R, and T are the same as above. But E here stands for natural base. And you can compute this only using your calculator. So e power x is the button you see on the calculator. And you really want to locate this button carefully. You have a lot of tutorials that will help you if you have difficulty with that, or you can come to the math lab and take some help there. Now, e power x is an inbuilt button. So, you know, you're recommended to use that. You must use that. But what is e? Well, E actually approaches the value 2.7. And there's a little bit of story to this. We will skip the story. But it was figured out that when you compound continuously, it doesn't give you some unnatural, unusually very large number. Actually, it always conforms to this particular value. Okay? So we have these two formulas, and we may be asked to call upon these two in this problem. So part A says to compound quarterly. So compounding quarterly means n is 4. Okay. If you can come up with a value for n, then you have to use the A equals P times 1 plus R over n power nt formula. So let's come to the problem and collect all the information we have. So let me highlight this. This is the amount invested, right? That is our P. And this 5% stands for the rate, rate of interest, which is 0.05. Remember to change it to decimal. And the duration of this investment is 18 years. That corresponds to the T. And for the first part, we got our N. So we're asked to find the future amount or the new balance in each case, right? So let's come here and plug them in. 10,000 times 1 plus 0.05 over n was 4, right? Quarterly. So that will be 4 times t is 18. Now it's time to simply use the calculator to compute this. Be very careful. I would suggest that you divide this into separate, smaller calculations. Don't plug them all into the calculator at the same time because you won't really be able to catch the errors. So now we have you know, what I mean is, like, I'm asking you to do this 0.05 over 4, 0.0125. and then do 4 times 18 for the power 72. Again, for those who know how to handle this, please do it confidently. If you are not sure, please take them step by step. So 1.0125 power 72. Now, when you bring it to this point, I would be cautious, so I will work backwards. So I will first do the power, meaning I will do 1.0125 power 72. Okay, that gives me a value 2.445920268 and so on. Okay, you keep that in the calculator. Okay, you don't have to clear that. You do that times 10,000. That gives you the final answer. 24459.20268. So that way you are not messing up or rounding too early. Okay, but remember A stands for the amount. So if it is the amount, the dollar amount, please remember to round it to the nearest cent. Put a comma there. 459 point. The nearest cent is always the second decimal place. 0.20. So if the grandfather invested this, or the grandparents invested this for a quarterly compounding, this is the money they will expect in 18 years. The 10,000 grows to this amount in 18 years. That makes perfect sense, right? If we messed up on the decimals anywhere, this number would look very weird, okay? It'd be totally absurd. So that's another way that you can catch any errors. All right, so next we have B, which is saying to compound monthly. If it's monthly compounding, n equals 12. So once again, we were able to fix a number for n, which means we're going to use the formula that involves n. And then let's plug in. All other details are the same. Only our n changes. The whole power n is 12 and t is still 18. So go ahead and do the computation. So I get this value after computation. But again, you want to round it appropriately. Nobody is going to tell you to round to the nearest cent. But you know that it's automatically the way we do it if we are dealing with money-related problems. So that's going to be 0.08. You can see that when it was compounded, when the frequency of the way it was compounded increased, the money also increased, right? Slightly, but definitely an increase. And then lastly, C was compounded to compound continuously. Compound continuously, that is your keyword, okay? Continuous compounding means you will have E involved in the formula. Continuous means E must be there because E is called the natural log. Oops. It is related to anything that happens naturally, right? Anything related to life. So we're going to use A equals P E power RT. So we'll do 10,000. E power R is 0.05 times T is 18. Here again, tread cautiously. I'm going to show each part what answer you get so that when you are computing at your end, you can compare your answers with me. So when you multiply the powers, you get 0.9 for E. Right? And then I'm using the E button in my calculator, and I do E power, and there is a box to enter the power at my end. So I enter 0.9, sorry. So 10,000, I'm still not multiplying the 10,000, okay? This E power 0.9 gives me a number like this, 459603111, okay? Now, ideally, you'll keep this as you see in the calculator and multiply this 10,000 to that number. That gives me 24596.03111. Right, it's again, 10,000 is just moving 4 decimal places to the right, so it's okay if you didn't even use the calculator, right? So I just moved it 4 places to the right. Anyway, so that's $24596.03 rounded to the nearest cent. As you can see, out of the 3 options, this gave them the best yield. But just because it was compounded continuously, things didn't spiral out of control. Like he didn't invest 10,000 in 18 years, got a new balance of 2 billion or million, right? It is still very close in comparison to the computation. But this is what it means, right? In real life, things are controlled. It's not, way out of control. So this is continuous compounding. This is the best compounding result. I hope this was helpful. I will see you in the next video.